Hello there, and welcome to our journey through one of science's most intriguing recent discoveries. Tonight, we will explore something that might change how we think about life in our solar system. We are going to discover the story of a single rock on Mars, a formation that has captured the attention of scientists around the world and sparked conversations about ancient life on our neighboring planet. This is not a story about dramatic announcements or definitive proof, but rather about careful scientific investigation, the patient accumulation of evidence, and the thoughtful questions that emerge when we examine the traces left behind by billions of years of planetary history. We will explore how a robotic explorer, no larger than a small car, discovered patterns in Martian stone that suggest something remarkable may have happened in that world's ancient past. We will learn about the careful process scientists use to interpret these findings and why this discovery represents both an exciting possibility and a reminder of how much we still have to learn about life beyond Earth. Before we begin, I would love to know where you are listening from tonight. Perhaps you are in a quiet room, maybe lying back with your eyes closed, contemplating the vast universe that surrounds us. No matter where you are, we share this moment together, floating on our small planet while considering the possibility that we may not be alone in our solar system. If you find these kinds of quiet explorations of scientific discovery interesting, I would be grateful if you could subscribe or like this program. It helps this gentle signal reach other curious minds who might enjoy these peaceful journeys through recent developments in space science. Take a moment now to settle in. Let your thoughts slow down to match the patient rhythm of scientific discovery, where answers emerge gradually through careful observation and thoughtful analysis. Tonight, our exploration focuses on Perseverance rover's remarkable finding in a location scientists have named Shayava Falls, and what this discovery might teach us about the ancient history of Mars and the possibility that microbial life once existed there. On a summer day in July 2024, something extraordinary happened in a quiet corner of Mars. The Perseverance rover, no larger than a small car, was making its methodical way across the rust-colored landscape when its cameras detected an unusual rock formation. Scientists believe this moment marked a turning point in humanity's search for life beyond Earth. The location held particular significance in the geography of Mars. Narrativa Vallis stretches across the Martian surface like a fossilized river carved by ancient waters that once rushed toward Jezero crater. Research suggests this valley system transported sediments and organic materials across the planet's surface more than 3 billion years ago, when Mars possessed a thicker atmosphere and liquid water flowed freely across its terrain. Perseverance had spent nearly 4 years traversing this alien landscape. The rover moved with deliberate precision through a world of silent stone and endless horizons. Evidence indicates that every carefully planned movement brought the mission closer to answering one of science's most profound questions: did life ever exist on our neighboring planet? The target that captured the rover's attention stood apart from its surroundings. Scientists later named this rock formation Shayava Falls, after a location in Arizona's Grand Canyon. The boulder measured approximately 3 meters long and 2 meters wide, shaped like a massive arrowhead pointing towards some unknown destination. Its surface displayed an intricate pattern of colors that immediately caught the attention of mission specialists back on Earth. Observations reveal that this single rock contained multiple geological stories: streaks of red indicated iron-rich mudstone, while purple bands suggested the presence of iron and phosphorus compounds. Green and yellow regions hinted at iron and sulfur minerals, creating a natural artwork painted by chemical processes that unfolded over geological timescales. The rover's operators faced a critical decision. Perseverance carried sophisticated drilling equipment capable of extracting core samples from Martian rocks, but each sample represented a precious opportunity. The mission could collect only 30 such specimens, and scientists believe careful selection would prove crucial for understanding Mars's ancient history and potential for harboring life. Mission controllers spent weeks analyzing the rock's composition from orbit. They examined high-resolution images transmitted across the vast distance between Mars and Earth, a journey that required radio signals to travel for more than 20 minutes at the speed of light. Evidence suggests that Chiava Falls possessed characteristics unlike any previously encountered during the mission. The decision to drill came after extensive deliberation. Research indicates that the rover's instruments detected organic carbon signatures within the rock's structure, compounds that could potentially indicate biological processes. Scientists approach this finding with appropriate caution, understanding that organic molecules can form through non-biological processes as well as through the activities of living organisms. On July 21st, Perseverance began the delicate process of extracting a core sample. The rover extended its robotic arm and positioned the drilling mechanism against the rock's surface. Scientists believe this procedure represents one of the most technically challenging aspects of Mars exploration, requiring precise control across millions of miles of space. The drilling process unfolded over several hours. Perseverance's diamond-tipped drill bit carved slowly through the ancient stone, extracting a cylindrical core roughly the thickness of a human finger. The sample measured approximately 6 centimeters in length, small enough to fit within a specially designed titanium storage tube, but large enough to contain potentially revolutionary information about Mars's biological history. As the drill penetrated deeper into Chiava Falls, it exposed interior layers that had remained hidden from Mars's harsh surface environment for billions of years. Evidence indicates these protected regions might preserve chemical signatures or structural features that could reveal whether microbial life once thrived in the planet's ancient lakes and rivers. The extracted core displayed remarkable characteristics under close examination. Scientists observed distinct patterns resembling what they informally termed leopard spots, circular reaction fronts, where different minerals had formed through chemical interactions. Research suggests these patterns might indicate locations where organic matter once reacted with iron-bearing compounds in the presence of water. Mission specialists sealed the precious sample within its titanium container, officially designating it Sapphire Canyon. The tube joined a growing collection of Martian specimens awaiting eventual return to Earth, where advanced laboratory instruments could conduct analyses far beyond the capabilities of any robotic explorer. Scientists believe this sample might contain the strongest evidence yet discovered for ancient life on Mars. The significance of this discovery extended beyond the physical characteristics of the rock itself. Observations reveal that Chiava Falls formed in an environment that researchers consider ideal for preserving signs of ancient biological activity. The fine-grained mudstone structure would have provided excellent conditions for entombing microscopic organisms or their chemical signatures within the geological record. Weather conditions on Mars during the drilling operation remained stable. The planet's thin atmosphere generated minimal wind, and temperatures held steady near negative 60 degrees Celsius. Evidence suggests these harsh surface conditions actually helped preserve the sample by preventing contamination from atmospheric moisture or terrestrial microorganisms that might confound future analysis. The rover's scientific instruments continued gathering data throughout the sampling process. Cameras documented every aspect of the procedure, while spectrometers analyzed the chemical composition of freshly exposed rock surfaces. Scientists believe this comprehensive documentation will prove essential for interpreting laboratory results when the sample eventually reaches Earth. Communication delays between Mars and Earth added complexity to the operation. Controllers on our planet could not provide real time guidance to Perseverance during critical moments of the drilling sequence. Research indicates that the rover's autonomous systems performed flawlessly, executing pre programmed instructions with mechanical precision while scientists waited anxiously for updates from across the solar system. The successful completion of the sampling procedure marked a milestone in robotic exploration. Evidence suggests that Perseverance had achieved something unprecedented in the history of space exploration, the collection of material that might contain direct evidence of extraterrestrial life. The implications of such a discovery would fundamentally alter humanity's understanding of biology, evolution, and our place in the cosmic order. As July 24th drew to a close on Mars, Perseverance sealed the Sapphire Canyon sample and prepared for its next phase of exploration. The rover would continue its journey across the ancient landscape, but scientists believe the events of that summer day might ultimately prove to be among the most significant in the annals of space exploration. The sample now rests safely within its titanium tube, protected from the Martian environment, while awaiting the complex mission that will eventually bring it home to Earth. Observations reveal that this tiny piece of stone, extracted from a quiet canyon on a distant world, might hold answers to questions that have fascinated humanity since we first gazed upward at the star-filled sky. 3.7 billion years ago, when Earth's earliest life forms were taking their first tentative hold in primordial seas, Mars told a different story altogether. The planet that we know today as a cold, rust-colored desert was then a world transformed by flowing water. Studies show that during this distant epoch, known as the Noachian period, Mars possessed something that would seem impossible to modern observers: vast lakes, meandering rivers, and perhaps even northern oceans that stretched across continents. Jezero Crater stands as one of the most remarkable witnesses to this ancient aquatic era. Located just north of the Martian equator, this impact basin stretches 45 kilometers across its weathered rim. Investigations reveal that this crater once cradled a lake system so extensive that it may have persisted for millions of years, receiving sediments and nutrients from a network of tributaries that carved channels across the surrounding highlands. The story of Jezero begins with violence, as do most Martian geological tales. Nearly 4 billion years ago, an asteroid or comet slammed into the planet's surface with tremendous force. The impact excavated a circular depression and sent shockwaves rippling across the landscape. Research indicates that such catastrophic events were commonplace during Mars' early history, when debris from the solar system's formation still roamed through interplanetary space. What happened next transformed the sterile impact scar into something extraordinary. As Mars's ancient climate permitted liquid water to exist on its surface, precipitation began to fill the crater basin. It appears that water arrived through multiple pathways, each contributing to the growing lake system that would eventually define Jazero's unique character. The northern and western rims of the crater display clear evidence of ancient inlet channels, waterways that once transported sediment laden rivers from the surrounding terrain into the waiting lake. The western inlet, known today as Naretva Vallis, carved the most dramatic pathway into Jazero. This ancient river system stretched for hundreds of kilometers across the Martian highlands, collecting water and sediments from a drainage basin that may have rivaled Earth's major river systems in scope. Evidence indicates that Naretva Vallis maintained a steady flow for extended periods, suggesting that Mars possessed a robust hydrological cycle during its early history. As water from Naretva Vallis entered Jezero crater, it encountered the relatively still waters of the ancient lake. The sudden decrease in velocity caused the river to deposit its cargo of sand, silt, and organic matter in a fan-shaped formation that geologists call a delta. Observations reveal that this delta grew steadily over time, building outward into the lake as countless floods delivered new sediments to its advancing front. The Jezero Delta displays characteristics that immediately capture the attention of planetary scientists. From orbital imagery, the formation resembles a bird's foot extending into the crater, with multiple channels radiating outward from the river's mouth. This distinctive morphology indicates that the delta formed under specific conditions, requiring a balance between sediment supply and lake levels that persisted for substantial periods. Ground-penetrating radar data from the Perseverance rover has provided unprecedented insights into the internal structure of these ancient deposits. Studies show that the delta contains horizontal layers of sediment, precisely the type of regular stratification that forms when particles settle through still water. These layers represent individual depositional events, each recording a moment when the ancient river carried sediments into the waiting lake. The thickness of these sedimentary layers varies significantly, suggesting that the river's flow patterns changed over time. Investigations reveal periods of steady, moderate discharge, alternating with episodes of intense flooding. This pattern reflects the complex climate dynamics that governed ancient Mars, where seasonal variations and longer-term climatic shifts influence the planet's water cycle. Evidence indicates that Jezero's lake experienced dramatic fluctuations in water level throughout its history. During high water periods, the lake may have reached depths of 30 meters or more, covering an area comparable to some of Earth's Great Lakes. The shoreline would have extended far beyond the delta deposits, creating extensive shallow water environments where different types of sediments accumulated. Lower water levels exposed portions of the lake floor, allowing erosional processes to carve channels through previously deposited sediments. It appears that these episodes of lake level decline were followed by renewed filling, creating a complex stratigraphic record that preserves evidence of Mars' changing climate. Each cycle of filling and draining left its signature in the geological record, creating the layered deposits that we observe today. The mineralogy of Jazero's sediments tells another compelling chapter of this ancient story. Research suggests that the crater's deposits contain significant quantities of clay minerals, particularly smectite clays, that form only in the presence of liquid water. These minerals require specific chemical conditions to develop, including neutral to slightly alkaline pH levels and temperatures above the freezing point of water. The presence of carbonate minerals within the delta deposits provides additional evidence for Mars' ancient habitability. Studies show that carbonates form when carbon dioxide dissolves in water, creating conditions that could support microbial life on Earth. Similar environments serve as nurseries for diverse biological communities, from microscopic bacteria to complex multicellular organisms. Investigations reveal that the sediments entering Jezero crater came from diverse geological sources. The drainage basin of Neretva Vallis included both volcanic terrains and older crustal rocks, providing a rich mixture of minerals and potentially organic compounds. This geological diversity would have created chemical gradients within the lake, establishing distinct microenvironments that might have supported different types of microbial communities. The longevity of Jezero's lake system represents one of its most astrobiologically significant characteristics. Evidence indicates that liquid water persisted in the crater for periods measured in millions of years, providing stable conditions for any potential life forms to establish themselves and evolve. Such temporal stability contrasts sharply with Mars's modern environment, where liquid water can exist only briefly under very specific conditions. The end of Jezero's aquatic era came gradually as Mars's climate shifted toward its current cold, dry state. Research suggests that atmospheric loss to space and the gradual cooling of the planet's interior combined to reduce the availability of liquid water on the surface. The rivers that once fed the crater's lake system began to flow less frequently and eventually ceased altogether. During the final phases of lake activity, dramatic flood events carved channels through the delta deposits. It appears that these late-stage floods resulted from the sudden release of water stored as ice or in underground reservoirs. The erosional features created by these events remain visible today, preserving evidence of Mars's transition from a world of lakes and rivers to the frozen desert we observe now. The sedimentary archives preserved within Jezero crater represent an invaluable record of Mars's climatic history. Studies show that these deposits contain chemical signatures that could reveal details about ancient atmospheric composition, seasonal temperature patterns, and the duration of habitable conditions. Each layer of sediment represents a snapshot of environmental conditions during a specific period in Martian history. As we examine Jezero's ancient lake system today, we glimpse not just the history of a single crater, but the biography of an entire planet. Evidence indicates that similar lake systems existed across Mars during the Noachian period, creating a network of potentially habitable environments that may have supported widespread microbial ecosystems. The story preserved in Jezero's sediments whispers of a time when Mars resembled Earth more than it resembles itself today, when the red planet was blue with water and possibly green with life. Scientists have long understood that rocks preserve stories within their crystalline structures, and mineral arrangements lie chronicles of ancient environments, chemical reactions, and perhaps even biological processes that unfolded across geological timescales. In July 2024, when Perseverance encountered the distinctive patterns within Shayava Falls, researchers realized they were witnessing one of the most compelling narratives ever discovered on another world. The markings that captured immediate attention appeared deceptively simple at first glance. Small circular features dotted the rock's surface in seemingly random distributions, creating patterns that mission scientists informally nicknamed leopard spots. Observations suggest these formations represent far more than mere aesthetic curiosities. They may constitute physical evidence of chemical processes that once sustained microbial ecosystems in ancient Martian environments. Each spot measured only millimeters across, yet their significance extends far beyond their modest dimensions. Research indicates that these circular structures formed through processes known as reaction fronts, locations where different chemical environments meet and interact within solid rock. Such boundaries represent zones of intense molecular activity, places where electrons transfer between compounds and new minerals crystallize from solution. The geometry of these features tells its own story. Studies show that the spots display concentric arrangements with darker outer rings surrounding lighter interior cores. This bullseye pattern suggests that chemical gradients developed within the rock, creating distinct zones where different reactions proceeded at varying rates. The precise circular symmetry indicates that the processes occurred under stable conditions over extended periods. Advanced spectroscopic analysis revealed the mineralogical composition of these intriguing formations. Evidence indicates that the spots contain significant concentrations of two iron-bearing minerals, vivianite and greigite. The presence of these specific compounds immediately captured the attention of astrobiologists, as both minerals form under conditions that frequently involve biological activity on Earth. Vivianite, chemically known as hydrated iron phosphate, displays a distinctive blue-green coloration when freshly exposed to air. Investigations reveal that this mineral typically forms in environments rich with organic matter, particularly in waterlogged sediments where oxygen levels remain low. On our planet, vivianite commonly appears in peat bogs, lake bottoms, and other locations where decaying plant and microbial materials create reducing chemical conditions. The formation of vivianite requires specific environmental parameters. Research suggests that phosphate ions must be available in solution, while iron exists primarily in its reduced ferrous state rather than the oxidized ferric form that creates rust. These conditions develop naturally when organic compounds consume dissolved oxygen through decomposition processes, creating the chemically reducing environments where vivianite can precipitate. Greigite presents an equally compelling case for potential biological involvement. This iron sulfide mineral forms through bacterial processes in many terrestrial environments. Studies show that certain microorganisms, particularly sulfate-reducing bacteria, generate greigite as a byproduct of their metabolic activities. These microscopic organisms derive energy by using sulfate compounds as electron acceptors, producing hydrogen sulfide gas that subsequently reacts with available iron to form greigite crystals. The coexistence of vivianite and greigite within the same rock formation creates a particularly intriguing scenario. Evidence indicates that both minerals form through electron transfer reactions involving organic matter and dissolved metals. On Earth, such mineral assemblages typically develop in sedimentary environments where microbial communities process organic compounds and alter the surrounding chemical conditions through their metabolic activities. The spatial distribution of these minerals within the leopard spots reveals additional details about their formation history. Observations suggest that the two compounds do not occur randomly throughout the rock, but instead concentrate in specific zones within each circular feature. This segregation implies that distinct chemical microenvironments existed within individual spots, possibly reflecting different stages of mineral precipitation or varying local conditions during formation. Detailed imaging of the reaction fronts shows that they cut across pre-existing rock textures. Research indicates that these chemical boundaries formed after the original sediment had been deposited, but before the rock underwent significant compaction and cementation. This timing suggests that the reactions occurred while the sediment retained sufficient porosity to allow fluid flow and chemical exchange between different regions. The size distribution of the leopard spots provides clues about the timescales involved in their formation. Studies show that larger spots tend to occur in areas where the rock displays coarser grain sizes, while smaller features appear in more fine-grained regions. This correlation suggests that the rate of reaction front propagation depended on the permeability of the surrounding sediment matrix. Chemical analysis of the areas surrounding the spots reveals elevated concentrations of organic carbon compounds. Evidence indicates that these organic molecules may have served as electron donors in the reactions that produced the observed mineral assemblages. The spatial correlation between organic matter and the iron-bearing minerals strengthens the hypothesis that biological processes influence the formation of these features. The morphology of terrestrial biosignature patterns provides important context for interpreting the Martian observations. Research suggests that microbial communities on Earth commonly create circular or ring-shaped features in sedimentary rocks through their metabolic activities. These biological structures, known as microbial mats or biofilms, can influence local chemical conditions and promote specific types of mineral precipitation. Comparative studies of ancient Earth rocks show remarkable similarities to the patterns observed in Shayava Falls. Investigations reveal that Precambrian sedimentary formations frequently contain circular features with mineral compositions and spatial arrangements analogous to the Martian leopard spots. These terrestrial examples formed in shallow marine or lacustrine environments, where microbial communities thrived in organic-rich sediments. However, distinguishing between biological and non-biological origins for such features remains challenging. Evidence indicates that certain geochemical processes can produce circular patterns and mineral assemblages similar to those created by microbial activity. High-temperature fluid flow, for example, can create reaction fronts and metal sulfide deposits that superficially resemble biological signatures. The temperature history of the Shayava Falls rock provides crucial constraints on possible formation mechanisms. Studies show that the sediment never experienced significant heating after deposition, ruling out high-temperature geochemical processes as explanations for the observed features. The absence of thermal alteration suggests that any reactions must have proceeded under relatively low temperature conditions more consistent with biological activity. Organic geochemistry offers another avenue for investigating the origin of the leopard spots. Research indicates that specific types of organic compounds preferentially form through biological processes, while others can arise through purely chemical reactions. Future analysis of the organic matter within the spots may reveal molecular signatures that could help discriminate between biological and abiological formation pathways. The preservation potential of microbial biosignatures provides important context for evaluating the Martian evidence. Evidence indicates that organic compounds and mineral textures can persist for billions of years under appropriate conditions. The fine-grained nature of the Shayava Falls rock would have provided excellent preservation conditions, protecting delicate structures from erosion and chemical alteration. The discovery of leopard spots in relatively young Martian sediments challenges previous assumptions about the planet's habitability history. Research suggests that signs of ancient life were most likely to be preserved in the oldest rocks, formed during Mars's early wet period. The presence of potential biosignatures in younger formations implies that habitable conditions may have persisted longer than previously believed. Understanding the formation mechanisms of these patterns requires consideration of the broader geological context. Studies show that the Neretva Vallis region experienced multiple episodes of water flow and sediment deposition over extended periods. Each cycle of environmental change would have created new opportunities for chemical reactions and potentially biological colonization. The complexity of the reaction patterns suggests that multiple processes operated simultaneously during their formation. Evidence indicates that the spots developed through a sequence of chemical reactions rather than a single precipitation event. This multi-stage formation history implies that stable conditions persisted long enough for complex chemical systems to develop and evolve. As we examine these enigmatic patterns today, we confront fundamental questions about the nature of life and its detection beyond Earth. Observations reveal that the leopard spots represent one of the most compelling examples of potential biosignatures yet discovered on Mars, displaying characteristics that strongly suggest biological involvement while acknowledging alternative explanations remain possible. The story written in stone across these ancient patterns speaks of a time when Mars may have harbored microbial communities in its sedimentary environments. Research indicates that these tiny features preserve evidence of chemical processes that could have sustained life billions of years ago, offering tantalizing glimpses of a biologically active past on our neighboring planet. What transforms lifeless rock into a repository of ancient secrets? Within the Shayava Falls sample, two remarkable minerals hold answers to this question, their molecular structures preserving chemical fingerprints that may chronicle microbial activities from billions of years past. These compounds, vivianite and greyjit, represent far more than simple geological curiosities. They constitute potential archives of biological processes that once flourished in Mars's primordial environments. Vivianite presents itself as one of nature's most intriguing mineral witnesses. This iron phosphate compound displays a distinctive blue-green coloration when exposed to oxygen, earning it recognition among terrestrial geologists as a marker of specific environmental conditions. Scientific studies demonstrate that vivianite formation requires a precise combination of chemical parameters, including abundant ferrous iron, dissolved phosphate ions, and most critically, oxygen-depleted conditions where organic matter undergoes decomposition. The molecular structure of vivianite tells a compelling story of its origins. Each crystal contains 8 water molecules bound within its lattice, creating the chemical formula iron 3 phosphate 8 hydrate. Research findings suggest that this hydrated structure forms exclusively in waterlogged environments where reducing conditions prevail. The mineral's distinctive blue appearance results from electron interactions within iron atoms, creating optical properties that serve as indicators of the chemical environment during formation. Laboratory investigations reveal that vivianite commonly develops in terrestrial peat bogs, wetlands, and lake sediments where organic materials accumulate faster than they decompose. Scientific observations indicate that bacteria play crucial roles in creating the chemical conditions necessary for vivianite precipitation. These microorganisms consume dissolved oxygen while breaking down organic compounds, establishing the reducing environment where ferrous iron remains stable and available for phosphate mineral formation. The formation mechanism of vivianite requires understanding of complex biogeochemical cycles. Research demonstrates that dissimilatory iron-reducing bacteria actively participate in vivianite development by using ferric iron compounds as electron acceptors during metabolic processes. As these organisms oxidize organic carbon, they reduce iron from its oxidized ferric state to the dissolved ferrous form, making it available for reaction with phosphate ions released during organic matter decomposition. Phosphate availability represents another critical factor in vivianite formation. Scientific studies show that phosphorus concentrations must reach specific thresholds before vivianite precipitation can occur. In natural systems, this phosphate often originates from decaying plant materials, animal remains, or microbial biomass. The phosphorus released during decomposition processes provides the building blocks necessary for vivianite crystal growth. Grey presents an equally fascinating case for potential biological involvement in mineral formation. This iron sulfide compound possesses the chemical formula iron 3 sulfur 4, making it the sulfur analog of the familiar iron oxide magnetite. Research findings indicate that Grey formation occurs predominantly through bacterial sulfate reduction processes, where specialized microorganisms derive energy by converting sulfate compounds into hydrogen sulfide gas. The crystal structure of Greyjet reveals important clues about its formation environment. Scientific observations demonstrate that this mineral adopts a cubic arrangement of iron and sulfur atoms, creating magnetic properties that distinguish it from other iron sulfide compounds. The mineral's magnetic characteristics have made it valuable for paleomagnetic studies, as Greyjet crystals can preserve records of ancient magnetic field orientations. Sulfate-reducing bacteria serve as the primary biological agents responsible for Greyjet formation in terrestrial environments. Laboratory studies show that these microorganisms thrive in oxygen-free conditions, using sulfate ions as alternative electron acceptors when oxygen becomes unavailable. During this metabolic process, bacteria produce hydrogen sulfide gas that subsequently reacts with dissolved iron to precipitate various iron sulfide minerals, including Greyjet. The transformation pathway from initial iron sulfide precipitation to Grey formation involves multiple steps. Research indicates that bacteria initially produce maconite, a simpler iron sulfide mineral with the formula iron sulfur. Over time, under specific conditions involving continued bacterial activity, maconite undergoes transformation to Grey through sulfur addition reactions. This process requires sustained microbial activity and stable environmental conditions over extended periods. Temporal factors play crucial roles in gragite development. Scientific studies demonstrate that the transformation from maconite to gragite typically occurs over months to years in laboratory settings, suggesting that natural gragite formation requires persistent bacterial activity. The slow kinetics of this transformation process imply that gragite presence indicates sustained reducing conditions and ongoing microbial metabolism over significant timescales. The coexistence of vivianite and gragite within the same rock formation creates particularly compelling evidence for biological involvement. Research findings suggest that both minerals form through electron transfer reactions mediated by organic compounds and bacterial activity in terrestrial environments. Their simultaneous occurrence typically indicates complex microbial ecosystems where different bacterial groups process various electron acceptors, creating chemical microenvironments that promote diverse mineral precipitation. Earth based analogs provide crucial context for interpreting the Martian mineral assemblage. Scientific observations from peat bogs, lake sediments, and wetland environments show that vivianite and gragite commonly form in organic rich waterlogged conditions where bacterial communities thrive. These terrestrial examples demonstrate that the mineral combination observed in Shayava Falls represents conditions strongly associated with biological activity on our planet. The preservation potential of these minerals offers important insights into their significance as biosignature indicators. Laboratory studies demonstrate that both vivianite and gragite remain stable under the chemical conditions that have prevailed on Mars since the sample's formation. The fine-grained mudstone matrix of Chayava Falls would have provided excellent protection from oxidation and dissolution, preserving delicate mineral textures that might record ancient biological processes. Electron microscopy studies of terrestrial vivianite and gragite revealed distinctive morphological characteristics that result from their biological formation pathways. Research shows that bacterially mediated mineral precipitation often produces specific crystal habits, size distributions, and spatial arrangements that differ from purely chemical precipitation. The detailed examination of these textural features in the Martian sample may provide additional evidence for or against biological involvement. Chemical isotope analysis represents another avenue for investigating the biological origins of these minerals. Scientific studies indicate that biological processes often create distinctive isotopic signatures in sulfur and iron compounds that differ from purely geochemical processes. Future laboratory analysis of the Shayava Falls sample may reveal isotopic evidence that could help discriminate between biological and non-biological formation mechanisms. The thermodynamic stability of grydite has important implications for understanding its formation conditions. Recent research demonstrates that grydite represents a stable phase in the iron-sulfur system at ambient temperatures, contradicting earlier assumptions that it formed only as a metastable intermediate. This stability indicates that grydite can persist indefinitely under appropriate conditions, making it a reliable indicator of past sulfate-reducing bacterial activity. Organic geochemistry provides additional context for understanding vivianite and gragite formation. Scientific studies show that specific organic compounds preferentially associate with these minerals during their formation. The organic carbon detected within the leopard spots of Shaiva Falls may represent remnants of the biological materials that originally facilitated mineral precipitation, preserved within the crystal lattices for billions of years. The spatial distribution of Vivianite and gray gist within the Shava Falls sample reveals important information about their formation history. Research findings suggest that the minerals concentrate in specific zones corresponding to ancient chemical gradients within the sediment. This distribution pattern implies that local variations in bacterial activity, organic matter content, or geochemical conditions influenced mineral precipitation on microscopic scales. Understanding the formation timescales for these minerals helps evaluate their significance as biosignature indicators. Laboratory studies demonstrate that vivianite can precipitate relatively rapidly once appropriate chemical conditions develop, while gragite formation requires more extended periods of bacterial activity. The presence of both minerals suggests that suitable conditions persisted long enough for complex biogeochemical processes to unfold and create lasting mineral evidence. The environmental conditions necessary for vivianite and gragite formation provide insights into ancient Martian habitability. Scientific observations indicate that both minerals require liquid water, organic matter, and specific chemical conditions that overlap significantly with requirements for microbial life. Their presence in Shayava Falls suggests that ancient Mars possessed environmental characteristics capable of supporting bacterial ecosystems similar to those found in Earth's anaerobic environments. Temperature constraints on mineral formation offer additional clues about the conditions during their precipitation. Research demonstrates that both vivianite and gragite form readily at temperatures consistent with those experienced by the Shayava Falls rock throughout its history. The absence of high temperature alteration features in the sample supports formation through low temperature biogeochemical processes rather than purely geochemical reactions. The discovery of these minerals in relatively young Martian rocks challenges assumptions about the planet's biological potential. Scientific studies previously focused on the oldest Martian formations as the most likely locations for preserved biosignatures. The presence of potential biological indicators in younger rocks suggests that habitable conditions may have persisted longer than previously believed, expanding the temporal window for possible life on Mars. As we examine these molecular messengers from ancient Mars, we encounter compelling evidence for processes that mirror biological activity on Earth. Research indicates that vivianite and gragite formation through purely chemical pathways would require conditions unlikely to have existed in the Shayava Falls environment. The minerals instead tell tales of iron dreams and phosphate stories, narratives written in crystal lattices that may preserve the chemical signatures of Mars' most ancient inhabitants. Picture a mountain climber ascending toward a distant summit, each foothold carefully tested before committing full weight to the next step upward. In the realm of astrobiology, scientists have constructed their own climbing framework, a methodical progression of evidence and verification designed to prevent catastrophic falls from overconfident claims. This systematic approach, known as the confidence of life detection scale, provides 7 distinct levels that researchers must navigate before declaring victory in humanity's greatest quest. The development of this framework emerged from decades of scientific lessons learned through ambitious claims and subsequent disappointments. Astrobiologists recognized that extraordinary discoveries require extraordinary evidence, particularly when those discoveries could fundamentally alter our understanding of life's cosmic distribution. Prior investigations, from meteorite analyses to planetary observations, demonstrated how easily initial excitement could transform into measured skepticism as additional scrutiny revealed alternative explanations for compelling observations. Level 1 represents the foundation of this methodical ascent. Research teams must demonstrate they have detected a possible signal that merits further investigation. This initial threshold requires documented observations that display characteristics potentially consistent with biological processes. The Shayava Falls sample crossed this benchmark when Perseverance's instruments identified organic carbon signatures alongside distinctive mineral formations that resembled patterns associated with microbial activity on Earth. Scientific protocols demand rigorous documentation at this preliminary stage. Mission specialists must provide detailed descriptions of their observations, including precise measurements, environmental context, and instrumental parameters. The data undergoes initial peer review within the research team, ensuring that preliminary interpretations rest on solid analytical foundations rather than wishful thinking or pattern recognition errors that can plague complex investigations. Level 2 introduces the critical requirement of contamination control. Scientists must demonstrate that their signal originates from the target environment rather than from terrestrial sources introduced during sample collection, processing, or analysis. This verification process represents one of the most technically challenging aspects of astrobiology research, as Earth-based microorganisms and organic compounds can infiltrate even the most carefully controlled systems. The Sapphire Canyon sample currently resides at this second level of confidence. Mission engineers implemented stringent contamination protocols throughout the sampling procedure, from sterilizing drilling equipment to sealing the core within titanium tubes under Martian atmospheric conditions. However, definitive contamination exclusion requires comprehensive laboratory analysis that can only occur when the sample returns to Earth-based facilities. Terrestrial contamination presents multifaceted challenges for life detection investigations. Microorganisms from Earth can survive extended periods in spacecraft environments, potentially compromising samples collected on distant worlds. Similarly, organic compounds associated with spacecraft materials or human handling can introduce false signals that mimic biological signatures. Advanced analytical techniques can sometimes distinguish between indigenous and contaminant sources, but this discrimination often requires molecular level analysis capabilities that exceed current robotic mission capacities. Level 3 establishes habitability requirements for the environment where the potential signal originated. Scientists must demonstrate that the location possessed physical and chemical conditions capable of supporting biological processes at the time when the putative biosignature formed. This assessment involves reconstructing ancient environmental parameters, including temperature ranges, water availability, chemical compositions, and energy sources that could have sustained metabolic activities. The Jezero crater environment meets many Level 3 criteria based on extensive geological evidence for ancient aquatic conditions. Research indicates that the region once hosted a substantial lake system with neutral pH conditions, moderate temperatures, and abundant organic compounds delivered through tributary networks. These parameters align closely with requirements for microbial communities observed in terrestrial environments, suggesting that ancient Mars possessed suitable conditions for biological activity. Environmental reconstruction requires interdisciplinary collaboration among geologists, chemists, and climate modelers. Teams analyze mineral assemblages, sedimentary structures, and atmospheric evolution models to characterize ancient conditions with sufficient precision for habitability assessments. This comprehensive approach helps eliminate environments where purely chemical processes might produce biosignature like patterns without requiring biological intervention. Level 4 presents, perhaps, the most intellectually demanding challenge on the confidence scale. Scientists must systematically consider and exclude alternative non biological explanations for their observed signal. This process requires exhaustive evaluation of potential abiotic mechanisms that could produce similar chemical signatures, mineral patterns, or structural features without involving living organisms. The requirement for comprehensive alternative hypothesis testing reflects hard-learned lessons from previous astrobiology investigations. Multiple instances have demonstrated how initial biological interpretations subsequently yielded to more mundane geological or chemical explanations once research communities conducted thorough evaluations. These experiences reinforce the principle that biological explanations should serve as hypotheses of last resort rather than default interpretations for unusual observations. Evaluation of abiotic alternatives demands extensive knowledge of geochemical processes, mineral formation mechanisms, and environmental chemistry. Research teams must collaborate with specialists from diverse fields to ensure comprehensive coverage of possible non-biological explanations. This collaborative approach helps prevent tunnel vision that might overlook obvious alternative explanations outside the investigator's primary expertise areas. Level 5 requires identification of additional independent signals that support the biological interpretation. Single observations, regardless of their apparent strength, rarely provide sufficient evidence for extraordinary claims in astrobiology. Multiple lines of evidence create redundant verification pathways that strengthen overall conclusions while reducing dependence on individual measurements that might suffer from unknown systematic errors or alternative interpretations. Independent evidence might include complementary chemical signatures, additional mineral associations, or morphological features that collectively support biological origin hypotheses. The spatial correlation of different biosignature types strengthens interpretive confidence by demonstrating that multiple biological indicators occur together in ways consistent with microbial ecosystem functioning rather than coincidental abiotic processes. The search for corroborating evidence often drives follow-up investigations using different analytical techniques or targeting related sample locations. This expansion of investigative scope helps establish whether initial observations represent isolated anomalies or components of broader patterns that strengthen biological origin hypotheses. Systematic surveys can reveal whether potential biosignatures occur in expected geological contexts or display distributions that support biological interpretations. Level 6 demands that research teams address alternative hypotheses specifically developed by the broader scientific community in response to initial biosignature claims. This requirement acknowledges that scientific peer review often generates novel explanations that original investigators might not have considered. Community scrutiny brings diverse expertise and fresh perspectives that can identify previously overlooked explanatory mechanisms. The peer review process operates as a crucial quality control mechanism in astrobiology research. Independent experts evaluate methodological approaches, analytical procedures, and interpretive frameworks with skeptical objectivity that helps identify potential weaknesses or alternative explanations. This external evaluation provides essential verification that strengthens credible claims while exposing flawed reasoning or inadequate evidence. Community generated hypotheses often emerge through conference presentations, workshop discussions, or informal scientific communications that occur before formal publication. These interactions allow researchers to test their interpretations against expert knowledge from related fields, potentially revealing explanatory mechanisms that interdisciplinary collaboration might uncover. The iterative nature of this process helps refine both evidence quality and interpretive frameworks. Level 7 represents the summit of the confidence mountain, requiring independent confirmation of life detection claims by separate research teams using different analytical approaches or sample materials. This final verification step acknowledges that extraordinary claims demand extraordinary verification through replication studies that demonstrate the reproducibility and robustness of initial findings. Independent confirmation serves multiple critical functions in establishing scientific consensus. First, it verifies that initial observations represent genuine phenomena rather than analytical artifacts or systematic errors specific to particular laboratories or instruments. Second, it demonstrates that biological interpretations remain valid under different analytical conditions or when applied to related samples from similar environments. The requirement for independent confirmation reflects broader scientific principles regarding reproducibility and peer verification. Major scientific breakthroughs typically undergo extensive replication efforts by independent research groups before achieving widespread acceptance within relevant scientific communities. This process helps distinguish genuine discoveries from experimental anomalies or interpretive errors that might initially appear convincing. Patience emerges as perhaps the most essential virtue throughout this methodical ascent toward certainty. Each level requires careful documentation, peer review, and community evaluation that unfolds over months or years rather than days or weeks. The timeline for comprehensive life detection verification often spans multiple mission cycles, requiring sustained commitment from research teams and funding agencies. The deliberate pace of this verification process frustrates public expectations for rapid answers to profound questions. Media coverage and public interest often focus on initial announcements rather than the subsequent years of careful analysis required for definitive conclusions. Scientists must balance transparent communication about preliminary findings with appropriate caution about premature claims that might later require revision. Current assessments place the Shayava Falls discovery at level 2 of this confidence framework, having demonstrated preliminary signal detection and implemented contamination control protocols. Progress to higher levels awaits comprehensive laboratory analysis of the returned sample, systematic evaluation of alternative explanations, and community peer review of detailed findings. The methodical nature of this progression ensures that eventual conclusions rest on solid evidential foundations rather than hopeful speculation. As we observe this careful scientific choreography, we witness more than mere bureaucratic procedure. The confidence ladder represents humanity's collective wisdom about the extraordinary nature of life detection claims and the extraordinary evidence required to support them. Each step upward brings us closer to answering fundamental questions about our cosmic solitude, but only through the patient accumulation of evidence that can withstand the most rigorous scrutiny science can provide. To Bull de Beeve, beneath the surface of a peaceful meadow, where sunlight never penetrates and oxygen becomes a distant memory, an extraordinary community of organisms transforms the very chemistry of their world. These microscopic architects, working in darkness and silence, demonstrate metabolic strategies that challenge our basic assumptions about life's requirements. Their ancient techniques for harvesting energy from iron and sulfur compounds may illuminate the nature of potential microbial communities that once flourished in the waterlogged sediments of ancient Mars. Terrestrial extremophiles occupy environments that mirror many conditions believed to have existed on early Mars. Studies reveal that these remarkable organisms thrive in locations where traditional life forms cannot survive, extracting energy from chemical reactions that most creatures would find toxic. Their metabolic versatility allows them to flourish in settings characterized by extreme acidity, high salinity, crushing pressure, or complete absence of oxygen. Iron reducing bacteria represent particularly relevant analogs for understanding potential Martian life. Research demonstrates that these microorganisms use ferric iron compounds as electron acceptors during cellular respiration, transforming oxidized iron minerals into dissolved ferrous iron through metabolic processes. This electron transfer generates the energy needed for growth and reproduction while creating chemical signatures that could persist in sedimentary rocks for billions of years. The biochemical pathways employed by iron reducing bacteria involve complex protein machinery that facilitates electron transport across cellular membranes. Scientific investigations show that these organisms produce specialized cytochromes and iron sulfur proteins that enable direct interaction with mineral surfaces. Such extracellular electron transfer allows bacteria to access iron locked within solid mineral lattices, expanding their potential energy sources beyond dissolved compounds. Sulfate reducing bacteria employ equally sophisticated strategies for anaerobic respiration. Laboratory studies demonstrate that these microorganisms convert sulfate ions into hydrogen sulfide gas while oxidizing organic compounds for carbon and energy. The metabolic process requires specialized enzymes that catalyze multi-step reduction reactions, transforming sulfur from its highest oxidation state to its most reduced form. The environmental requirements for sulfate reduction align remarkably well with conditions inferred for ancient Martian lake systems. Research indicates that these bacteria thrive in waterlogged sediments, where organic matter accumulates and oxygen levels remain low. The presence of dissolved sulfate, abundant organic compounds, and neutral to slightly alkaline pH conditions provides optimal settings for bacterial communities to establish themselves and flourish. Methanogenic archaea demonstrate another metabolic strategy that could have operated on early Mars. Scientific observations reveal that these microorganisms produce methane gas through carbon dioxide reduction, using hydrogen gas as an electron donor. This process, known as methanogenesis, represents one of the most ancient forms of metabolism on Earth and requires only simple inorganic compounds that would have been readily available in Martian environments. The products of methanogenic activity create distinctive chemical signatures that persist long after the organisms themselves have died. Studies show that specific carbon isotope ratios in ancient rocks can indicate biological methane production, providing potential biosignature targets for future Mars exploration missions. The preservation of these isotopic signatures depends on rapid burial and protection from oxidation processes that could alter their original compositions. Chemolitho-autotrophic bacteria utilize inorganic electron donors such as hydrogen sulfide, ammonia, or ferrous iron to drive carbon fixation reactions. Research demonstrates that these organisms can survive in environments devoid of organic nutrients by constructing cellular components from carbon dioxide and simple inorganic compounds. This metabolic independence would have provided significant advantages in early planetary environments where organic matter remained scarce. The energy yields from chemolitho autotrophic metabolism are typically lower than those from organic respiration, requiring bacterial communities to process large quantities of inorganic substrates to support growth and reproduction. Scientific calculations indicate that such metabolic strategies could sustain microbial ecosystems even in nutrient poor environments, provided adequate supplies of appropriate electron donors and acceptors remained available. Nitrate reducing iron oxidizing bacteria present particularly compelling analogs for potential Martian life. Laboratory investigations show that these organisms can couple ferrous iron oxidation to nitrate reduction under anoxic conditions, generating energy while producing ferric iron minerals and nitrogen containing gases. The discovery of nitrate deposits on Mars suggests that suitable electron acceptors may have been available to support such metabolic processes. The pH tolerance ranges of extremophilic bacteria encompass conditions likely to have existed in ancient Martian water bodies. Research reveals that many species can function across pH ranges from moderately acidic to alkaline conditions, adapting their cellular chemistry to maintain internal homeostasis despite external fluctuations. This physiological flexibility would have enhanced survival prospects during periods of environmental change on Mars. Temperature requirements for extremophilic growth align well with thermal conditions inferred for ancient Mars. Scientific studies demonstrate that psychrophilic bacteria can remain active at temperatures near the freezing point of water, while thermophilic species tolerate conditions approaching boiling temperatures. This broad temperature tolerance suggests that microbial communities could have persisted across diverse thermal environments on early Mars. Salinity tolerance represents another crucial factor for potential Martian life. Research shows that halophilic bacteria can survive in brines containing salt concentrations several times greater than seawater, maintaining cellular function through specialized osmotic regulation mechanisms. The presence of sulfate and chloride salts in Martian soils suggests that hypersaline conditions may have been common in ancient surface waters. Desiccation resistance mechanisms allow certain extremophiles to survive extended periods without liquid water. Scientific observations reveal that some bacteria can enter dormant states during dry conditions, resuming metabolic activity when water becomes available again. This survival strategy could have enabled microbial communities to persist through periods when surface water became scarce on Mars. Radiation tolerance varies significantly among extremophilic species, with some organisms demonstrating remarkable resistance to ionizing radiation levels that would quickly kill most life forms. Laboratory studies show that DNA repair mechanisms, protective pigments, and antioxidant compounds enable survival under high radiation conditions similar to those on the Martian surface. The spatial distribution of extremophilic communities in terrestrial environments provides insights into potential colonization patterns on Mars. Research demonstrates that bacterial populations often concentrate near chemical interfaces where different electron donors and acceptors meet, creating localized zones of enhanced metabolic activity. Similar chemical gradients would have developed in ancient Martian sediments, potentially supporting distinct microbial communities. Seasonal variations in extremophilic activity reflect responses to changing environmental conditions. Scientific monitoring reveals that bacterial metabolic rates fluctuate in response to temperature changes, water availability, and nutrient supply variations. Such seasonal cycles would have occurred on ancient Mars due to orbital variations and climatic fluctuations, influencing microbial community dynamics. Symbiotic relationships among different microbial species create complex ecosystems in extreme environments. Studies show that metabolic products from one bacterial group often serve as substrates for other organisms, establishing intricate food webs based on chemical cycling rather than photosynthetic primary production. Similar cooperative relationships could have developed in ancient Martian ecosystems. Biomineralization processes, catalyzed by extremophilic bacteria, produce mineral deposits that preserve evidence of biological activity. Research demonstrates that bacterial metabolism can influence crystal nucleation, growth rates, and morphology of precipitating minerals, creating distinctive textures that distinguish biologically mediated mineralization from purely chemical processes. The preservation potential for extremophilic biosignatures depends on burial conditions and post-depositional chemical changes. Scientific studies indicate that rapid burial in fine-grained sediments provides optimal conditions for preserving cellular structures, organic compounds, and mineral textures associated with microbial activity. The sedimentary environment of Jezero Crater would have provided excellent preservation conditions for any microbial communities that developed there. Modern analogs for potential Martian ecosystems exist in various terrestrial environments, including deep subsurface aquifers, hypersaline lakes, acid mine drainage systems, and hydrothermal springs. Research at these locations reveals diverse microbial communities adapted to conditions that closely resemble those inferred for ancient Mars, demonstrating that life can indeed flourish under such extreme circumstances. As we contemplate the hidden world of Earth's extremophiles, we encounter organisms whose very existence expands our conception of life's possibilities. Scientific evidence demonstrates that these remarkable microbes employ metabolic strategies perfectly suited to the chemical conditions that once prevailed in Martian lake systems, suggesting that similar communities might have established themselves in the ancient sediments of Jezero Crater. Their modern descendants continue their invisible work in Earth's most challenging environments, living testimonies to life's extraordinary adaptability and persistence across our solar system's diverse worlds. Sealed within its titanium chamber, A fragment of Mars waits in exile beneath alien skies. The Sapphire Canyon sample, no larger than a pencil's width, yet potentially containing answers to humanity's most profound questions, rests in engineered isolation on the surface of a world that once knew flowing rivers and thriving lakes. This tiny core, extracted from the arrowhead-shaped boulder known as Chayava Falls, represents both culmination and beginning dense, the endpoint of years of meticulous exploration, and the starting point for revelations that may reshape our understanding of life itself. The titanium tube containing the sample represents a masterpiece of engineering precision designed to protect its precious cargo across impossible distances and decades of time. Mission engineers selected titanium alloys for their exceptional corrosion resistance, mechanical strength, and chemical inertness that would prevent contamination of the enclosed material. The tube's walls, measuring only millimeters in thickness, must withstand temperature extremes, pressure variations, and physical stresses that would challenge much thicker containers. Creating a hermetic seal under Martian conditions required innovative solutions to problems never before encountered in space exploration. Engineering teams developed specialized ferrules and activation mechanisms that could create gas-tight seals using mechanical compression rather than traditional welding or adhesive techniques. The sealing process relied on precisely controlled forces applied by robotic mechanisms to deform metal components into leak-proof configurations. The titanium nitride coating applied to the tube's interior surface serves multiple critical functions in sample preservation. This golden-colored ceramic layer provides exceptional chemical stability while resisting interaction with organic compounds that might be present in the rock sample. Laboratory testing demonstrated that the coating remains stable across temperature ranges from minus 150 degrees Celsius to plus 150 degrees Celsius, encompassing all conditions the sample might experience during its journey. Helium leak testing verified the integrity of sealed sample tubes using detection methods sensitive to leak rates, measured in cubic centimeters per second, multiplied by scientific notation factors, approaching the theoretical limits of measurement precision. These extraordinarily low leak rates ensure that atmospheric gases captured with the rock sample will remain uncontaminated by external sources throughout the planned return mission timeline. The sample preservation protocol begins immediately after drilling operations conclude on the Martian surface. Perseverance's robotic systems transfer the core material directly from the drill bit into the waiting titanium tube without exposing it to ambient atmospheric conditions. This direct transfer minimizes contamination risks while preserving any volatile compounds or atmospheric gases that might accompany the solid sample. Automated sealing procedures execute with mechanical precision designed to eliminate human error possibilities. The rover's sample handling assembly positions the ferrule within the tube's mouth and applies carefully calibrated compression forces to create the hermetic seal. Multiple sensors monitor the sealing process to verify proper ferrule placement and adequate compression levels before finalizing the containment. Temperature monitoring throughout the sampling and sealing procedures ensures that thermal conditions remain within acceptable limits for sample preservation. Engineering specifications establish maximum allowable temperatures during drilling operations to prevent thermal alteration of organic compounds or mineral phases that might provide evidence of biological processes. The fine-grained mudstone of Chayava Falls proved particularly suitable for low-temperature sampling techniques. The sealed tube joins a growing collection of Martian specimens awaiting eventual return to terrestrial laboratories. Each container bears unique identification markers and detailed documentation of sampling conditions, drilling parameters, and environmental circumstances during collection. This comprehensive record keeping enables scientists to interpret analytical results within appropriate geological and environmental contexts. Storage conditions on Mars present ongoing challenges for sample preservation over extended time frames. The tubes must withstand daily temperature cycles ranging from minus 80 degrees Celsius during winter nights to plus 20 degrees Celsius during summer afternoons. These thermal fluctuations create expansion and contraction stresses that could compromise seal integrity over multi-year storage periods. Radiation exposure represents another preservation concern for samples stored on the Martian surface. Cosmic rays and solar particle events bombard the planet continuously, potentially inducing chemical changes in organic compounds or mineral structures within the sample tubes. Calculations indicate that radiation doses remain below levels that would significantly alter most geological materials, but subtle effects on complex organic molecules remain possible. The sample's location within Perseverance's adaptive caching assembly provides some protection from environmental extremes. The rover's body shields the stored tubes from direct wind exposure and abrasive dust storms that could physically damage external surfaces. Internal heating systems help moderate temperature fluctuations, though they cannot completely eliminate thermal cycling effects. Dust accumulation poses additional challenges for long-term sample storage on Mars. Fine particulates carried by frequent dust storms can infiltrate mechanical systems and potentially compromise sealing mechanisms if preventive measures prove inadequate. Engineering teams incorporated dust protection features throughout the sample handling systems to minimize these risks. The chemical environment within the sealed tube creates a unique microworld isolated from Mars's oxidizing surface conditions. Any water vapor, organic compounds, or reactive gases captured during sampling remain trapped within the titanium container, potentially undergoing slow chemical interactions over extended storage periods. These processes could either preserve or alter evidence of ancient biological activity, depending on specific reaction pathways. Trace contamination from terrestrial sources represents a constant concern throughout sample handling operations. Despite rigorous sterilization procedures, some Earth-derived organic compounds or microorganisms might survive within the sampling systems and contaminate the Martian material. Advanced analytical techniques will be required to distinguish indigenous Martian signatures from potential terrestrial contaminants. The sample's crystalline and mineral structures face potential alteration during extended storage periods. Phase transitions, recrystallization processes, or chemical reactions between different mineral components could modify the sample's original characteristics. However, the relatively stable conditions within the sealed tube should minimize such changes compared to exposure on the open Martian surface. Organic preservation within the sample depends on multiple factors, including pH conditions, moisture content, and the presence of catalytic mineral surfaces. Laboratory studies of terrestrial analogs suggest that fine-grained sedimentary rocks provide excellent preservation conditions for organic compounds over geological timescales. The Shiva Falls sample's mudstone composition appears well suited for maintaining organic integrity. The anticipated timeline for sample return creates pressure for optimal preservation throughout the waiting period. Current mission planning suggests that retrieval operations might not occur for another decade or more, requiring the samples to maintain their scientific integrity across extended storage periods. Engineering analyses indicate that properly sealed tubes should preserve their contents throughout such timeframes. Advanced laboratory facilities on Earth await the sample's eventual arrival with analytical capabilities far exceeding those of any robotic explorer. Electron microscopy, mass spectrometry, and isotopic analysis techniques will enable detailed examination of mineral textures, organic compounds, and potential biosignature materials at resolutions impossible to achieve with rover-mounted instruments. The sample's scientific value extends beyond immediate biological questions to encompass broader understanding of Martian geological processes, atmospheric evolution, and environmental history. Detailed mineralogical analysis will provide insights into ancient water chemistry, temperature conditions, and geochemical processes that shape the planet's surface environment during its potentially habitable period. As the Sapphire Canyon sample continues its patient vigil beneath Martian skies, it embodies humanity's boldest scientific aspirations, wrapped in titanium and hope. Engineering excellence has created conditions for preserving whatever secrets this small fragment of alien stone might contain, protecting them from the passage of time and the harsh realities of interplanetary space. In laboratories yet to be built, using techniques yet to be perfected, scientists will eventually unlock the stories written in its crystalline structure and mineral arrangements, possibly revealing whether Earth stands alone or shares the cosmos with other worlds that once harbored life. How does a machine perceive the chemical signatures of ancient life across the void of interplanetary space? The answer lies within the sophisticated array of scientific instruments mounted on Perseverance rover, electronic extensions of human curiosity that can detect molecular compositions, mineral arrangements, and elemental distributions with precision that surpasses many earthbound laboratory techniques. These robotic senses have transformed a collection of rocks and sediments into detailed chemical narratives that chronicle Mars's biological potential across billions of years. The Planetary Instrument for X-ray Lithochemistry, known by its acronym PIXEL, serves as one of Perseverance's most powerful analytical tools for detecting potential biosignature minerals. This X-ray fluorescence spectrometer operates by directing high-energy X-ray photons at rock surfaces, causing atoms within the target material to emit characteristic fluorescent radiation that reveals their elemental composition. The technique allows scientists to map chemical distributions at microscopic scales, identifying zones where specific elements concentrate in patterns that might indicate biological processes. Pixel's detection of iron and phosphorus concentrations within the leopard spots of Shiva Falls provided crucial evidence supporting the biosignature hypothesis. The instrument's analysis revealed elevated levels of these elements in circular patterns that suggested localized chemical reactions had occurred within the ancient sediment. The spatial correlation between iron-rich and phosphorus-rich zones created geochemical signatures consistent with microbial electron transfer processes observed in terrestrial environments. The instrument's microcontext camera captures detailed images of rock textures and surface features before and after X-ray analysis, providing visual documentation of target areas at resolutions approaching 10 micrometers per pixel. These high magnification images reveal structural details invisible to human eyes, including grain boundaries, fracture patterns, and mineral relationships that help scientists interpret chemical data within appropriate geological contexts. Pixel's operational parameters require careful optimization for each target analysis. The instrument must balance exposure times, beam intensities, and spatial sampling strategies to maximize data quality while minimizing analysis duration and power consumption. Typical scanning procedures involve systematic movement of the X-ray beam across target surfaces in grid patterns, collecting spectra from hundreds or thousands of individual points to create comprehensive elemental maps. The scanning habitable environments with Raman and luminescence for organics and chemicals instrument, abbreviated as Sherlock, employs laser spectroscopy techniques to identify organic compounds and minerals associated with aqueous alteration processes. This deep ultraviolet spectrometer uses laser excitation to stimulate molecular vibrations and electronic transitions that produce distinctive spectral signatures characteristic of specific chemical compounds. Sherlock's laser operates at wavelengths near 248 nanometers, energies sufficient to excite both Raman scattering and luminescence phenomena in target materials. The instrument can distinguish between different types of organic molecules based on their unique vibrational fingerprints, while also identifying minerals that form through water-rock interaction processes. This dual capability enables comprehensive characterization of both organic and inorganic components within individual rock samples. The detection of organic carbon signatures within Chiava Falls required careful analysis to distinguish genuine Martian organic compounds from potential terrestrial contamination sources. Sherlock's spectroscopic data revealed carbon-bearing molecules distributed throughout the rock sample in patterns that correlated with mineral assemblages rather than random contamination distributions. This spatial relationship supported interpretations that the organic compounds originated from Martian sources rather than spacecraft-related contamination. Luminescence signals detected by Sherlock provided additional evidence for organic matter within the sample. When excited by ultraviolet laser radiation, certain organic compounds emit characteristic fluorescence at specific wavelengths that can be distinguished from mineral-based luminescence signals. The instrument identified multiple luminescence features within Chiava Falls that displayed spectral characteristics consistent with aromatic organic compounds. The Watson camera, formerly known as the Wide-Angle Topographic Sensor for Operations and Engineering, functions as Sherlock's companion imaging system. This color camera captures detailed photographs of rock surfaces at resolutions sufficient to resolve individual mineral grains and textural features. Watson images provide essential context for interpreting spectroscopic data by showing the physical relationships between different chemical phases within target rocks. Watson's imaging capabilities extend beyond simple photography to include stereo reconstruction techniques that create three-dimensional models of rock surfaces. These topographic maps enable scientists to measure surface roughness, identify layering patterns, and characterize erosional features that provide insights into environmental conditions during rock formation and subsequent alteration processes. Data processing and interpretation require sophisticated software systems capable of handling the enormous volumes of information generated by rover instruments. Each analytical session produces thousands of individual spectra, elemental maps, and contextual images that must be transmitted across interplanetary distances and processed by teams of specialists using advanced computational techniques. The integration of pixel and Sherlock data creates comprehensive chemical portraits of target rocks that exceed the analytical capabilities of either instrument operating independently. Correlation analysis between X-ray fluorescence and laser spectroscopy measurements enables identification of mineral phases, organic compounds, and their spatial relationships within individual samples. This multi-technique approach provides redundant verification of analytical results while revealing chemical associations that might escape detection by single instrument analyses. Signal to noise optimization represents a constant challenge for rover based spectroscopic measurements. Environmental factors, including temperature variations, dust accumulation, and mechanical vibrations, can introduce artifacts into spectral data that must be carefully distinguished from genuine chemical signatures. Calibration procedures using onboard reference materials help maintain analytical accuracy throughout the mission duration. The transmission of analytical data from Mars to Earth requires careful prioritization given limited communication bandwidth and scheduled contact windows. Mission planners must balance scientific priorities with data volume constraints, often requiring preliminary data processing on Mars to identify the most significant results for immediate transmission while archiving complete data sets for later retrieval. Quality control procedures ensure that instrumental measurements maintain accuracy and precision throughout extended operation periods on the Martian surface. Regular analysis of calibration standards, blank measurements, and duplicate analyses provides ongoing verification of instrumental performance while identifying potential degradation or contamination issues that might affect data quality. The environmental conditions on Mars create unique challenges for maintaining instrumental performance over multi-year mission durations. Temperature extremes, dust storms, and radiation exposure can gradually degrade sensitive electronic components or optical elements within scientific instruments. Engineering teams incorporated robust designs and protective features to maximize operational lifetimes under these harsh conditions. Power management represents another critical constraint for rover-based analytical operations. Each spectroscopic analysis consumes electrical energy from limited battery reserves that must also support rover mobility, communication systems, and other mission-critical functions. Operational planning requires careful balancing of scientific priorities with power availability to maximize mission productivity. The successful detection of potential biosignature minerals within Shayava Falls demonstrates the remarkable capabilities of modern robotic analytical systems. These instruments have achieved measurement precision and chemical specificity that rivals many terrestrial laboratory techniques, while operating autonomously on an alien world millions of miles from human oversight. Their electronic senses have extended human perception across the solar system, transforming distant rocks into detailed chemical landscapes that may hold keys to understanding life's cosmic distribution. Future analytical sessions will continue expanding our chemical knowledge of Mars through systematic investigation of diverse rock types and environmental settings. Each measurement adds to the growing database of Martian geochemistry that guides sample selection for future return missions while building comprehensive models of the planet's chemical evolution and biological potential. 40 million miles separate Mars from Earth when the two worlds achieve their closest orbital alignment. Yet this astronomical distance represents merely the beginning of the challenges facing humanity's most ambitious sample return mission. The delicate titanium tubes, containing potential evidence of ancient Martian life, must traverse not only the vast emptiness of interplanetary space, but also navigate an increasingly complex web of engineering constraints, budgetary limitations, and technological obstacles that threaten to delay their homecoming by decades. The original Mars sample return mission architecture called for an intricate choreography of multiple spacecraft working in perfect coordination across the inner solar system. Engineering teams envisioned a specialized sample retrieval lander that would collect the cached tubes from the Martian surface, transfer them to a powerful ascent vehicle capable of launching from Mars, and rendezvous with an orbiting spacecraft that would capture the samples and transport them safely back to Earth. This ambitious plan represented the most complex robotic mission ever attempted by any space agency. Budget projections for the mission have undergone dramatic escalation as engineering teams grappled with the unprecedented technical challenges. Initial cost estimates, near $5 billion, dollars, have swollen to projections exceeding $11 billion, dollars, as design reviews revealed the complexity of landing, launching, and orbital rendezvous operations required for mission success. These escalating costs threaten to consume resources needed for other critical scientific missions, forcing administrators to reconsider the entire mission architecture. The sample retrieval lander must accomplish tasks never before achieved by robotic systems operating on Mars. The spacecraft needs to locate cached sample tubes on the planet's surface, navigate to their storage locations with centimeter level precision, collect the containers using robotic manipulator arms, and transfer them to an ascent vehicle for launch back to orbital rendezvous points. Each of these operations presents unique engineering challenges that require development of entirely new technologies. Mars Ascent Vehicle development represents perhaps the most technically demanding aspect of the entire mission. No spacecraft has ever launched from the surface of Mars, requiring engineers to design rocket systems capable of operating in the planet's thin atmosphere while carrying precious cargo to orbital velocities. The ascent vehicle must function reliably, despite months or years of exposure to Martian environmental conditions, including temperature extremes, dust storms, and radiation bombardment. The European Space Agency's Earth Return Orbiter serves as the final link in the sample return chain, responsible for capturing the sample container in Mars orbit and transporting it across interplanetary space to Earth vicinity. This spacecraft must possess sufficient propulsive capability to escape Mars's gravitational influence, navigate precisely along the transfer trajectory, and execute complex orbital maneuvers required for Earth approach and sample capsule deployment. Timeline projections for sample return have shifted repeatedly as technical challenges accumulate and budget constraints force mission redesigns. Original plans for sample arrival in the early 2030s have given way to more realistic projections, placing return dates in the 2040s or potentially even later, depending on funding availability and technological development progress. These delays frustrate scientists eager to begin detailed laboratory analysis of potentially life bearing samples. Alternative mission architectures under consideration attempt to reduce costs and complexity while maintaining scientific objectives. One approach utilizes proven sky crane landing technology, similar to that employed by the Curiosity and Perseverance rovers, potentially reducing development risks associated with entirely new landing systems. Another concept involves commercial space companies providing heavy lift capabilities that could simplify mission design while reducing government development costs. Private industry involvement represents a potentially transformative approach to Mars sample return challenges. Companies developing heavy lift rockets and advanced propulsion systems might provide capabilities that government agencies cannot efficiently develop independently. This public private partnership model has proven successful for Earth orbital operations and might offer similar advantages for interplanetary missions. International cooperation remains essential for mission success despite growing technical and financial challenges. The partnership between NASA and the European Space Agency provides complementary capabilities and shared financial responsibilities that make the ambitious mission feasible. However, coordinating development schedules and technical requirements across multiple space agencies adds complexity to an already challenging endeavor. Planetary protection protocols create additional mission requirements that influence design decisions and operational procedures. The sample return spacecraft must prevent forward contamination of Mars during landing operations, while also ensuring that any potentially viable Martian microorganisms do not contaminate Earth's biosphere during sample handling procedures. These dual requirements demand sophisticated containment systems and sterilization procedures. The sample containment and handling systems must preserve the integrity of collected materials throughout the multi-year journey from Mars to Earth. Temperature control, radiation shielding, and mechanical shock absorption become critical engineering requirements for maintaining sample quality during launch, interplanetary cruise, and Earth approach phases of the mission. Any compromise in sample preservation could invalidate years of scientific effort. Risk assessment and mitigation strategies address the numerous failure modes that could jeopardize mission success. Single point failures in critical systems could result in complete loss of samples that represent years of Perseverance rover exploration and billions of dollars in mission investment. Redundancy and backup systems add mass, complexity, and cost, but provide essential insurance against component failures. Mission operations and ground support require unprecedented coordination between multiple control centers, managing different spacecraft elements simultaneously. Communication delays between Earth and Mars create autonomous operation requirements that exceed those of typical robotic missions, while orbital mechanics constraints limit communication windows and data transmission opportunities throughout the mission duration. Technology development timelines increasingly constrain mission scheduling as engineers discover that key systems require longer development periods than originally anticipated. Critical technologies, including Mars ascent propulsion, orbital rendezvous systems, and Earth entry vehicles, need extensive testing and validation before integration into flight hardware, extending overall mission development schedules. Budget allocation decisions must balance Mars sample return requirements against other high priority scientific missions competing for limited resources. Congressional funding constraints force mission planners to consider scaled back architectures that might compromise scientific objectives but remain within available budgets while preserving other important planetary science initiatives. The scientific value of returned samples provides compelling justification for overcoming technical and financial obstacles. Laboratory analysis capabilities on Earth far exceed those possible with robotic rovers, offering opportunities to detect subtle biosignatures, perform detailed isotopic measurements, and conduct microscopic examinations that could definitively resolve questions about ancient Martian life. These potential discoveries justify extraordinary efforts to ensure mission success. Public interest and political support fluctuate with changing budget priorities and competing national challenges. Maintaining long-term commitment to Mars sample return requires sustained advocacy for space science while demonstrating clear benefits that justify substantial public investment in fundamental research activities. Educational outreach and public engagement help build support for ambitious scientific endeavors. As mission planners struggle with engineering realities and budgetary constraints, the precious samples continue their patient wait on the Martian surface. Each passing year adds to the urgency of developing viable return architectures, while accumulated scientific knowledge from ongoing rover operations increases the potential value of detailed laboratory analysis. The samples represent not just pieces of ancient rock, but embodiments of humanity's deepest questions about our place in a potentially life-bearing cosmos. The eventual resolution of Mars sample return challenges will test humanity's commitment to scientific discovery and our willingness to invest in knowledge that transcends immediate practical concerns. Success would mark a pivotal moment in astrobiology and planetary science, while failure might delay fundamental advances in understanding life's cosmic distribution for generations to come. In the scorching waters of Yellowstone's hot springs, where temperatures approach the boiling point of water and acidity rivals that of battery acid, communities of microscopic organisms thrive in conditions that would instantly destroy most life forms. These remarkable ecosystems serve as natural laboratories for understanding how life might have emerged and persisted in the harsh environments of ancient Mars, providing tangible examples of biological processes operating under conditions once thought incompatible with living systems. Terrestrial Mars analog environments span the globe from polar deserts to deep ocean hydrothermal vents, each offering insights into different aspects of potential Martian habitability. Research teams have identified locations where combinations of temperature, chemistry, pressure, and radiation exposure create conditions remarkably similar to those inferred for various periods in Mars's environmental history. These analog sites enable controlled studies of biological processes under Mars-like conditions without the complexity and expense of interplanetary missions. The Atacama Desert of Chile represents one of Earth's most Mars-like environments, combining extreme aridity, high radiation exposure, and oxidizing soil chemistry that approaches conditions observed on the modern Martian surface. Scientific studies in this hyper-arid region reveal microbial communities that survive on minimal moisture while tolerating salt concentrations and oxidant levels that would be lethal to most organisms. These extremophile populations demonstrate biological strategies for persistence under conditions similar to those on contemporary Mars. Deep subsurface environments provide analogs for potential habitable zones beneath the Martian surface where liquid water might persist despite harsh surface conditions. Research in deep mines, aquifers, and geothermal systems reveals microbial ecosystems thriving kilometers below Earth's surface in environments characterized by high pressure, elevated temperature, and complete isolation from sunlight. These communities derive energy from chemical reactions involving rock water interactions, suggesting similar processes could support life in Mars' subsurface. Arctic permafrost regions offer insights into microbial survival strategies under freezing conditions with limited liquid water availability. Scientific investigations in these permanently frozen environments demonstrate that bacterial communities can remain viable for thousands or potentially millions of years in ice dominated conditions. Such persistence mechanisms could enable Martian microorganisms to survive extended periods of climatic change or seasonal freezing cycles. Acid mine drainage systems create chemical conditions that mirror the sulfate rich, low pH environments inferred for certain periods of Martian history. Research in these highly acidic waters reveals diverse microbial communities dominated by iron and sulfur oxidizing bacteria that transform mineral compositions through metabolic processes. The mineral precipitation patterns observed in these systems closely resemble features detected in Martian rocks by rover missions. Deep sea hydrothermal vents represent analogs for ancient Martian hydrothermal systems, where hot, mineral rich fluids interacted with surface or near surface environments. Scientific studies at these underwater oases reveal complex ecosystems based on chemosynthetic primary production rather than photosynthesis, demonstrating that life can flourish using energy from chemical reactions alone. Similar hydrothermal environments may have provided critical habitat for early life on Mars. Hypersaline lakes and salt deposits provide analogs for the highly saline conditions that likely characterized many Martian water bodies during the planet's aqueous period. Research in locations such as the Dead Sea, Great Salt Lake, and various salt flats reveals halophilic microorganisms adapted to extreme salinity levels. These organisms employ specialized biochemical mechanisms to maintain cellular function in environments where most life forms would rapidly dehydrate and die. Volcanic environments offer insights into microbial survival under high temperature conditions with active geochemical processes. Scientific investigations of volcanic hot springs, lava flows, and fumaroles reveal thermophilic communities that thrive in temperatures exceeding 70 degrees Celsius while tolerating toxic gas concentrations and rapid chemical changes. Such conditions may have been common near volcanic activity on early Mars. High altitude environments provide analogs for the low atmospheric pressure and enhanced radiation exposure that characterize the Martian surface. Research on mountain peaks in the upper atmosphere and in spacecraft environments reveals microbial adaptation strategies for surviving reduced atmospheric protection and increased cosmic radiation exposure. These studies inform assessments of surface habitability on Mars, both past and present. Cave systems represent analogs for potential subsurface habitable zones on Mars, where protection from surface conditions might enable microbial communities to persist. Scientific studies in deep caves reveal diverse ecosystems that develop in complete darkness while utilizing chemical energy sources derived from rock weathering and groundwater interactions. The stable environmental conditions in cave systems could provide refuge habitats during periods of climatic stress on Mars. Laboratory simulation experiments complement field studies at analog sites by enabling controlled manipulation of environmental parameters relevant to Martian conditions. Research teams use specialized chambers to recreate combinations of temperature, pressure, atmosphere composition, and radiation exposure that allow systematic investigation of microbial responses to Mars-like conditions. These experiments help identify the environmental limits for life and optimize strategies for detecting biosignatures. Survival experiments with Earth microorganisms exposed to simulated Martian conditions provide direct assessments of biological viability under alien environmental parameters. Scientific studies have demonstrated that various bacterial spores, vegetative cells, and extremophilic organisms can survive short-term exposure to Mars-like conditions, including low pressure, carbon dioxide atmosphere, and temperature fluctuations. Some organisms even remain viable during extended exposure periods, measured in months or years. Biomarker preservation studies at analog sites investigate how biological signatures degrade or persist under different environmental conditions relevant to Mars exploration. Research teams examine how organic compounds, mineral biosignatures, and cellular structures change over time when exposed to oxidation, radiation, temperature cycles, and chemical alteration processes similar to those occurring on Mars. These studies guide development of biosignature detection strategies for rover missions. Ecosystem structure analysis at analog sites reveals patterns of microbial community organization that might characterize life on Mars. Scientific investigations demonstrate how environmental gradients create distinct ecological niches supporting different types of organisms with complementary metabolic strategies. Understanding these community structures helps predict where life might concentrate on Mars and what signatures might indicate biological activity. Metabolic process studies examine the biochemical pathways that enable life to persist under Mars-like conditions. Research on anaerobic respiration, chemolithoautotrophy, and stress response mechanisms provides insights into potential energy sources and metabolic strategies that could support Martian life. These studies help identify chemical signatures that might indicate ongoing or ancient biological processes. Contamination control research at analog sites addresses challenges for distinguishing indigenous life from introduced organisms in Mars exploration scenarios. Scientific studies examine how terrestrial microorganisms spread in extreme environments and develop protocols for preventing contamination of samples during collection and analysis procedures. This research is essential for ensuring that any life detected on Mars represents genuine Martian biology. Environmental monitoring at long-term analog sites documents how microbial communities respond to environmental changes over extended time periods. Research teams track population dynamics, community composition, and biomarker production as environmental parameters fluctuate naturally or in response to experimental manipulations. These longitudinal studies provide insights into ecological stability and resilience under variable conditions. Technology testing at analog sites enables validation of instruments and techniques intended for Mars life detection missions. Research teams use field studies to optimize sample collection procedures, analytical protocols, and data interpretation methods under realistic environmental conditions. This testing helps identify potential problems and improve mission success probability before expensive spacecraft deployment. As we examine these remarkable terrestrial analogs, we encounter living proof that life's ingenuity extends far beyond familiar environments into realms once considered uninhabitable. The thriving communities in Earth's most extreme locations demonstrate biological strategies and survival mechanisms that expand our understanding of life's possibilities throughout the cosmos. These natural laboratories provide essential guidance for Mars exploration while revealing the extraordinary adaptability that has enabled life to colonize virtually every available niche on our home planet. 4.5 billion years ago, both Mars and Earth began their existence as molten spheres of rock and metal, condensing from the stellar nursery that would become our solar system. In those earliest epochs, the two worlds followed surprisingly similar evolutionary paths, developing atmospheres, oceans, and perhaps even the chemical conditions necessary for life's emergence. Yet somewhere in the depths of geological time, their destinies diverged dramatically, with Earth becoming a vibrant biosphere, while Mars transformed into the frozen desert we observe today. The Noachian period of Martian history, spanning from approximately 4.1 to 3.7 billion years ago, represents the planet's most Earth-like era. Geological evidence reveals that Mars possessed a thicker atmosphere dominated by carbon dioxide, with sufficient greenhouse warming to maintain liquid water on its surface, despite receiving less solar energy than Earth. Vast river systems carve networks of valleys across the planet's surface, while impact craters filled with water to create lakes and possibly even hemispheric oceans. The atmospheric modeling studies suggest that early Mars maintained surface pressures several times greater than modern values, creating conditions where liquid water could exist across broad temperature ranges. The planet's original atmosphere likely contained not only carbon dioxide, but also water vapor, nitrogen, and other gases that contributed to greenhouse warming effects. Volcanic outgassing from the planet's active interior continuously replenished atmospheric losses while delivering additional heat to surface environments. The magnetic field protection that Earth enjoys today was absent on early Mars due to the planet's smaller size and more rapid core cooling. Without a global magnetic field to deflect solar wind particles, Mars's atmosphere became vulnerable to gradual erosion by charged particle bombardment from the Sun. This process, known as atmospheric escape, slowly stripped away the protective envelope that enabled surface water to persist in liquid form. Volcanic activity on early Mars rivaled or exceeded that of Earth during comparable time periods, creating massive shield volcanoes and extensive lava plains that still dominate the planet's topography. The heat generated by radioactive decay within Mars's interior drove vigorous geological processes, including plate tectonics, though these systems operated differently than Earth's more familiar continental drift patterns. Volcanic outgassing released water vapor and other atmospheric components that maintained habitable surface conditions. The transition from warm, wet conditions to cold, dry environments occurred gradually over hundreds of millions of years as atmospheric loss processes exceeded replenishment rates. Solar wind erosion, preferentially removed lighter atmospheric components, including hydrogen, leading to progressive oxidation of surface materials and the development of iron oxide deposits that give Mars its characteristic red coloration. This gradual transformation trapped remaining water in subsurface ice deposits or seasonal frost cycles. Impact bombardment. During the late heavy bombardment period, approximately 3.9 billion years ago, delivered enormous quantities of water and organic compounds to both Mars and Earth. However, Mars's smaller gravitational field made it less efficient at retaining these volatile materials compared to Earth's stronger gravitational attraction. Many impact-delivered volatiles escaped back to space, limiting the accumulation of surface water reservoirs. Climate modeling indicates that early Mars experienced significant seasonal and longer-term variations in temperature and precipitation patterns due to orbital parameter changes and volcanic activity cycles. These climatic fluctuations would have created diverse environmental conditions ranging from warm, humid periods favorable for biological processes to colder, drier intervals that challenged any emerging life forms. Such variability might have driven evolutionary adaptation in potential Martian organisms. The planet's smaller mass and lower internal heat generation led to more rapid cooling of the interior and cessation of the geological processes that maintained atmospheric density. As volcanic activity declined, atmospheric replenishment rates decreased, while escape processes continued removing gases to space. The resulting atmospheric thinning reduced greenhouse warming and initiated a feedback cycle leading toward current conditions. Water cycle dynamics on early Mars likely resembled those of Earth, with evaporation from surface bodies, atmospheric transport, and precipitation creating active hydrological systems. Evidence for ancient river deltas, sedimentary deposits, and hydrated minerals indicates that water cycled between surface reservoirs, atmospheric vapor, and ground ice storage throughout the Noetian period. This active water cycle enabled chemical weathering and sediment transport processes. The chemical evolution of Mars' atmosphere involved complex interactions between volcanic outgassing, atmospheric escape, and surface mineral formation processes. Carbon dioxide from volcanic sources reacted with surface rocks to form carbonate minerals, while water interacted with basaltic compositions to produce clay minerals and other hydrated phases. These reactions gradually altered both atmospheric composition and surface mineralogy. Oxidation processes became increasingly dominant as atmospheric hydrogen preferentially escaped to space, leaving behind a progressively more oxidizing environment. Iron-bearing minerals transformed from reduced phases to oxidized forms, while any organic compounds faced increasingly challenging preservation conditions. This oxidation trend culminated in the formation of highly oxidizing surface materials observed by modern rover missions. Subsurface environments on Mars retained more stable conditions than surface locations as atmospheric changes progressed. Groundwater systems, protected from direct atmospheric loss, persisted longer than surface water bodies and provided potential refugia for any life forms that developed during more favorable earlier periods. Geothermal heating around volcanic centers could have maintained localized habitable zones, even as global conditions deteriorated. The preservation of ancient environmental records and Martian rocks provides direct evidence for the planet's climatic evolution. Sedimentary deposits, mineral assemblages, and isotopic signatures document changing conditions throughout geological history. These records enable reconstruction of temperature, atmospheric composition, and water availability during different periods of planetary evolution. Comparative planetology studies reveal that Mars' evolutionary pathway represents one possible outcome for terrestrial planets, while Earth's continued habitability required specific combinations of size, orbital characteristics, and geological processes. The divergent histories of these neighboring worlds highlight the complex interactions between planetary parameters and long-term environmental stability. The timing of Mars's climatic transition coincides with the period when life was becoming established on Earth, suggesting that any Martian biosphere would have faced increasing environmental stress during critical evolutionary phases. Organisms that developed during favorable early conditions would have needed remarkable adaptability to survive the transition to modern Martian conditions. Evidence for episodic water activity during later periods indicates that Mars's climatic evolution included temporary reversals toward more habitable conditions, orbital parameter changes, volcanic reactivation, or impact events might have periodically restored surface water activity, creating windows of opportunity for biological processes to resume or persist in refugia environments. Understanding Mars' transformation from a potentially habitable world to its current state provides crucial insights for assessing the habitability of exoplanets orbiting other stars. The Martian example demonstrates that early habitability does not guarantee long-term environmental stability, while also revealing the geological signatures that might indicate ancient habitable conditions on distant worlds. As we contemplate the slow death of Mars as a biosphere, we witness both tragedy and instruction in the planet's 4 billion-year journey from Eden to wasteland. The same processes that created favorable conditions for potential life ultimately destroyed those conditions through inevitable planetary evolution. Yet Mars's transformation preserved evidence of its habitable past in rocks and minerals that now guide our search for ancient life, while teaching us about the fragility and resilience of planetary environments throughout the cosmos. Standing at the threshold of perhaps the most profound discovery in human history, we find ourselves contemplating questions that have haunted our species since we first gazed upward at the star-filled darkness and wondered if we were alone. The Sapphire Canyon sample, sealed within its titanium tomb and waiting patiently on the Martian surface, may contain answers that fundamentally alter our understanding of life's place in the cosmic order, or it may deepen the mystery of our apparent solitude in a vast and seemingly empty universe. The implications of confirming ancient life on Mars extend far beyond academic curiosity or scientific achievement. Such a discovery would represent the first definitive evidence that biological processes operate beyond our home planet, transforming astrobiology from theoretical speculation into empirical science. Every assumption about life's rarity or commonality, every philosophical framework for understanding humanity's cosmic significance would require fundamental revision in light of concrete evidence for extraterrestrial biology. If the minerals and organic compounds within Shayava Falls prove to be genuine biosignatures, Mars becomes more than a neighboring planet and transforms into a second genesis, an independent origin of life that occurred in our own solar system billions of years ago. This revelation would suggest that life emerges readily whenever suitable conditions develop, implying that biological processes might be common throughout the galaxy's countless planetary systems. The search for life beyond Earth has driven scientific inquiry for centuries, yet until now we have possessed only theoretical frameworks and indirect evidence to guide our investigations. The potential biosignatures discovered by Perseverance represent the first tangible materials that might directly answer fundamental questions about life's cosmic distribution. Laboratory analysis of returned samples could provide definitive proof that biology operates as a universal phenomenon rather than a unique accident. Philosophical implications of discovering ancient Martian life challenge core assumptions about humanity's special status in the universe. Religious worldviews, scientific paradigms, and cultural narratives would all require reconsideration in light of evidence that Earth does not represent the sole abode of living systems. The uniqueness that has shaped human identity for millennia would give way to recognition that we are part of a broader biological community spanning multiple worlds. The scientific method itself would undergo transformation as researchers develop new frameworks for understanding biology in cosmic contexts. Comparative biology would expand beyond terrestrial species to encompass entirely alien evolutionary lineages, potentially revealing universal principles governing life's emergence and development. The discovery of Martian biosignatures would inaugurate new fields of study, including xenobiology and comparative planetary biology. Evolutionary biology would gain unprecedented perspectives through examination of independently evolved biological systems. If Martian life developed along pathways similar to terrestrial biology, it would suggest that evolutionary processes follow predictable patterns constrained by physical and chemical laws. Alternatively, fundamental differences between Earth and Mars life could reveal the extent of biological possibility and the role of contingency in shaping living systems. The origin of life question would shift from theoretical speculation to comparative analysis as scientists examine two separate examples of biogenesis occurring within the same stellar system. Common features between Earth and Mars biology might reveal universal requirements for life's emergence, while differences could illuminate the range of conditions and processes capable of generating living systems from non-living matter. Astrobiology research priorities would undergo dramatic reorientation towards systematic searches for life throughout the solar system and beyond. Evidence for ancient Martian life would justify massive investments in missions to Europa, Enceladus, Titan, and other potentially habitable worlds within our solar system. The search for biosignatures would become a central focus of planetary science, with implications for understanding habitability throughout the cosmos. Planetary protection protocols would require fundamental revision to address the reality of viable extraterrestrial biology. Current policies designed to prevent contamination would need updating to reflect confirmed biological diversity within the solar system. Future missions to Mars and other potentially inhabited worlds would operate under more stringent constraints to prevent both forward and backward contamination. The development of life detection technologies would accelerate dramatically with confirmation that biosignatures exist and can be preserved over geological timescales. Investment in sophisticated analytical instruments, sampling systems, and preservation techniques would increase as space agencies recognize the importance of detecting and characterizing extraterrestrial life forms throughout the solar system and beyond. Societal impacts of discovering ancient life on Mars would resonate through education, culture, and public policy as humanity adjusts to its new understanding of cosmic biology. Science education curricula would require updates to include comparative biology and astrobiology concepts, while cultural institutions would grapple with implications for art, literature, and philosophical traditions rooted in assumptions of terrestrial uniqueness. International cooperation in space exploration would likely increase as nations recognize shared interests in understanding life's cosmic distribution. The scientific and philosophical significance of studying extraterrestrial biology might provide common ground for collaborative missions and data sharing agreements that transcend political boundaries and foster global cooperation in scientific endeavors. However, the alternative scenario, the detailed analysis, reveals non biological explanations for the observed patterns in Shayava Falls, would carry equally profound implications for our understanding of life's cosmic status. Failed detection of genuine biosignatures would reinforce questions about life's rarity and the special conditions that enabled biology to emerge and persist on Earth while apparently failing on our neighboring planet. The absence of confirmed Martian life would focus attention on understanding why Earth succeeded in developing and maintaining biological systems, while Mars apparently failed despite similar early conditions. This comparative approach might reveal critical factors that determine planetary habitability and biological potential, providing insights essential for assessing life's prospects throughout the universe. Negative results would intensify searches for life in other solar system locations, while highlighting the challenges facing biological systems in planetary environments. The apparent failure of life to establish itself permanently on Mars might indicate that biology requires more specific conditions than previously assumed, suggesting that habitable worlds might be rarer than optimistic projections indicate. The question of statistical significance becomes paramount when considering life's cosmic distribution based on limited examples. A sample size of one habitable world provides insufficient data for assessing biological probability, while confirmation of independent biogenesis on Mars would double our statistical base and suggest that life emerges commonly under appropriate conditions. Future exploration strategies will be fundamentally shaped by whatever answers emerge from analysis of Martian samples. Confirmation of ancient life would justify ambitious searches throughout the solar system, while negative results might redirect efforts toward understanding Earth's unique biological success and searching for similar conditions around other stars. The timeline for obtaining definitive answers stretches years into the future as sample return missions navigate technical challenges and budgetary constraints. During this extended waiting period, scientists continue gathering evidence from rover missions while developing increasingly sophisticated theoretical frameworks for interpreting potential biosignature discoveries. As we stand at this pivotal moment in human knowledge, contemplating samples that might contain proof of ancient alien life, we confront the magnificent uncertainty that has always driven scientific inquiry. The Sapphire Canyon sample represents more than geological material. It embodies our deepest questions about existence, meaning, and our place in the cosmic story. Whether it confirms our cosmic companionship or reinforces our apparent solitude, its analysis will mark a watershed moment in humanity's quest to understand life's role in the universe and our own significance in the vast expanse of space and time. The question that remains is not merely whether life once existed on Mars, but what that answer reveals about the nature of existence itself and humanity's role in a cosmos that may teem with life or stand as a rare oasis of biology in an otherwise sterile universe.